Hey guys, today I want to present a solution to the China Team Selection Test 2018 Problem 2. At first, let's have a look on the problem statement. We are asked to find all positive integers k such that we find an arithmetic progression an equals to s plus kn such that 2018 divides d of an for every positive integer n. Here, d of an denotes the number of positive divisors of an. In order to get a better handling of this function here, our first step is to factor out the greatest common divisor of s and k in the sum here. So let us define g to be the greatest common divisor of s and k, and then we can define s prime to be s divided by g and k prime to be equal to k divided by g. Then we can write an to be equal to g times s prime plus k prime n. If we want to say something about the number of divisors of an, it would be nice if g and the sum here are co-prime. Therefore, our goal is to find some value for n such that this is indeed true. Here, Dirichlet's theorem is really helpful because it tells us that there are infinitely many numbers n such that the sum here is a prime number. And therefore, we can find some n such that s prime plus k prime n is equal to a prime number p, and this prime number p does not divide g. We want to use the fact that for co-prime numbers, the divisibility function is multiplicative. This can be directly seen by writing the formula down that d of n is equal to the product over all prime numbers p of nu p of m plus 1. So we get in this case that d of an is equal to d of g times d of p, and this is equal to d of g times 2. And now we use the fact that we want 2018 to divide d of an, and therefore we can conclude that 1009 divides d of g. In fact, 1009 is a prime number, and therefore, if we have a look back to this formula, we conclude that there exists a prime number, p1, such that nu p1 of g is congruent to minus 1 modulo 1009. This directly implies that nu p1 of g is greater than or equal to 1008. Since this congruence here, that nu p1 of g is congruent to minus 1 modulo 1009, should be true, it's a reasonable choice that we choose s in such a way that nu p1 of s is exactly 1008. Then we have that nu p1 of g is exactly equal to 1008, and s prime is not divisible by p1. And here we don't want that k prime is also not divisible by p1, because then we can choose n in such a way that the sum here is divisible by p1. So intuitively we are done if k is divisible by p1 by at least 1009 times, and otherwise we can get into trouble. And now let's try to formalize this. Let's start with the case that nu p1 of k is greater than or equal to 1009. So we can write k equals p1 to the power of 1009 times t. And moreover, as I said, we want to choose s in such a way that s is equal to p1 to the power of 1008 times u, and here we want that u is not divisible by p1. We get an is equal to p1 to the power of 1008 times u plus p1 times t times n. And now, since p1 does not divide u, we know that p1 and the sum here are co-prime, so we can conclude that d of an is equal to d of p1 to the power of 1008 times d of u plus p1 times t times n, and this is equal to 1009 times d of u plus p1 times t times n. To conclude that this product here is divisible by 2018, it's only left to prove that this second factor here is divisible by 2. This is equivalent to the fact that this term here is never be a perfect square. So if we can prove that this is not equal to a perfect square, then we would be done. If p1 is odd, we know that there are exactly p1 plus 1 over 2 quadratic residues modulo p1, and therefore we know that there is a not quadratic residue modulo p1. So we can choose u to be such a not quadratic residue, and therefore we know that this sum here can't be a perfect square, and therefore for p1 not equal to 2, we are done. In the case that p1 is equal to 2, we are done if we can find a prime number q not equal to 2 that divides t, because then we can find with the same argument a non-residue class modulo q for u. If t is a power of 2 not equal to 1, then we are also done in this case, because then p1 times t is divisible by 4, and then we can choose u to be equal to 3, which is a non-residue class modulo 4. So in total, if p1 equals to 2 and t greater than 1, we are also done. So we are done if we can find a prime number p1 such that nu p1 of k is greater than or equal to 1009 and k is not equal to 2 to the power of 1009. So let's write this down in orange and then consider the other cases. At first, we want to consider the case that k is equal to 2 to the power of 1009. And here we remember that we wanted nu p1 of g to be greater than or equal to 1008 for some prime number p1. And since 2 is the only prime number dividing k, this prime number p1 must be equal to 2. And therefore we know that also s must be divisible by 2 by at least 1008 times. So we can write s to be equal to 2 to the power of 1008 times u. This gives us that an is equal to 2 to the power of 1008 times u plus 2 times n. Here we can find a square number greater than u and with the same parity as u, and therefore we can find some positive integer n such that this sum here is a perfect square, and therefore in total an is equal to a perfect square, which means that the number of divisors of an is equal to an odd number, and therefore 2018 cannot divide d of an. So we conclude that k equals to 2 to the power of 1009 does not work. We are left with our last case, namely that nu p of k is less than or equal to 1008 for every prime number p. Since g divides k, this also implies that nu p of g is less than or equal to 1008. Recall that we already figured out that there exists a prime number p1 such that nu p1 of g is greater than or equal to 1008. Combined with this fact here, we can conclude that nu p1 of g is exactly equal to 1008. And therefore, we are motivated to consider all prime numbers, p1, p2, and so on up to pr, satisfying nu pi of g is equal to 1008. And as I already said, here we know that r is at least 1. From the fact that nu p of k is less than or equal to 1008, this directly implies that pi does not divide k prime. In other words, if I define p to be the product of all these prime numbers p1, p2 up to pr, we know that this capital P is co-prime to k prime. This means that there exists a multiplicative inverse of k prime modulo capital P, and therefore we know that there exists some L in the set from 1 up to capital P such that L is congruent to minus S prime divided by k prime modulo p. That implies capital P divides S prime plus k prime L. Therefore, we want to take a look at these terms here of this arithmetic progression where n is congruent to L modulo capital P. So let's have a look on them and let's call it A of n prime times capital P plus L. This is equal to G times S prime plus k prime times, and here we take this value for n, which is n prime times capital P plus L, and this is equal to G times S prime, and now we have plus k prime L, which is exactly this term here, and then a plus k prime times n prime times capital P. Since S prime plus k prime L is divisible by capital P, we can factor P out to get that this is equal to G times P times S prime plus k prime L over P plus k prime n prime. At this point, we know that the number of divisors of G times capital P is not divisible by 1009 because we know that nu pi of G times capital P is exactly equal to 1009, and moreover we have that nu p of G times capital P is less than or equal to 1007 for every prime number p which is not equal to a prime number pi. Therefore, it would be nice if we can use again Dirichlet's theorem to find some integer n prime such that the sum here is equal to a large prime number that does not divide G times P. So it is enough to prove that S prime plus k prime L divided by P and k prime are co-prime integers, because then we can indeed do this argument and are done. Let's calculate this greatest common divisor. Namely, we have that the GCD of S prime plus k prime L divided by P and k prime is equal to the GCD of S prime plus k prime L and k prime, because we know that capital P and k prime are co-prime integers, and this is now equal to the GCD of S prime and k prime, because we know that we can subtract a multiple of k prime from this left term here, and now we know that this is equal to 1 because we already assumed in the beginning that S prime is equal to S divided by G and k prime to k divided by G, where k is the greatest common divisor of S and k. So indeed, S prime plus k prime L divided by P and k prime are co-prime integers, and therefore we are done.